Hello, everyone. It's about 2:35, so I think we should start. Today, we will be having Peter Humburg speak with us as part of our monthly seminar series. For those of you who haven't joined us before, we do a monthly series of seminars throughout the year that focus on general basic statistical issues that researchers may encounter. And they are completely free and open to anyone who wants to attend. So you are always welcome to come. We at Stat Central are a group of consultants who help people with their research. And so we focus on helping people with research design, data analysis, and response to reviewers' comments on submitted articles or grant proposals. And we are a service that's available to HDR students at the university and also research staff as well. Each of us is associated with a particular school or unit in the university or in the clinical schools at UNSW. And so the people in those schools or units have a lot of access to our help. Otherwise, we have a general consulting service that many people at UNSW can contact us through for some help. So if you are interested in having some help and assistance in your research, let us know. We have a website, and you can fill out a request form there, and we'll get in contact with you and hopefully be able to help you out. Today, as I mentioned, we have Peter Humburg, who's one of our consultants. He works in our general consulting, and he works a lot of his time at NEURA. So much of his work has to do with them. He has a really great background in social sciences, so education, psychology, and also bioinformatics. So he's got quite a broad base of experience. And today's going to be talking to us about model selection and inference and how maybe we shouldn't actually do that. So go ahead, Peter. Thank you.
Thanks, Nancy. Hi, everyone. I hope you can hear me all right. So yes, today I would like to talk about an issue that comes up fairly frequently with researchers that come to talk to me to get some help. And that is that you may find yourself in a situation where you want to do model selection and then draw some inference from the resulting model. And so I would like to take some time today to talk about why that maybe is a bit of a problem, and a little bit about what you might be able to do about it. So what's going on? So when you run a research study, you might well find yourself in a situation where you run your study, you collect lots of data, one or more outcomes, and lots of other variables that may or may not be related to the outcomes you're interested in. And then once you've collected the data, you want to go and analyze it. And for the purpose of this seminar, I will assume that what you want to do is run a linear regression for simplicity's sake. And it is often something you do want to do, but similar considerations really apply to other types of analysis too. So you have lots of variables, and it's not really feasible to include all of them in the analysis. And there can be various reasons for that, right? I mean, there can simply be too many. If you have lots of variables and not actually that many participants or data points, then you can't just cram all of them in a model. It's not going to work. So you have to select some of them. It's also possible that you may be concerned about collinearity, because lots of the variables that you collected data for may be related measures of similar things, and so naturally they're correlated. And you may not want to include them into the model for that reason. And so it seems quite convenient to do some sort of model selection first to identify a subset of your variables that will actually do a good job at explaining the outcome you're interested in, and then use that to answer your research questions, right? There are various ways you can go about that. You might use backward selection or some form of penalized regression, or a number of different approaches are available, really. So there's quite a bit of choice. And that's the thing that people do, you may have done, and that's all fine. But the problem then arises if you want to go take that model there, where you've used your data to figure out, what's the best possible combination of variables to explain the outcomes I observe, and then want to actually use that for inference and get some answers, right? This is a problem that people have known about for quite a while. So here's a quote I pulled from a paper that's about 30 years old now, but it was far from the first to point out the issue. And yeah, so the fundamental problem is that once you've looked at your data to figure out some clever combination of variables to model your outcomes, simply going and applying your traditional inference method, that is, taking your linear regression fit and basically looking at the coefficients to see whether they are statistically significant or not. That doesn't really make sense anymore. And yeah, that seems a bit unfortunate, because looking at this, strictly speaking, it seems like you can't have both, right? So if you ask yourself, can I go figure out what a good model looks like and then draw some conclusions from that same model? The answer very clearly seems to be no. And yeah, that's not really an answer that a lot of people are happy with, I guess, because, well, you do want those answers, right? And so really the question is, well, what can we do? And as a first step to answering that question, it might make sense to look a bit at the problem in more detail, right? So what I want to do is take a closer look at what actually happens when you do this, right? What happens when you sort of mix your model selection and inference together? So to get a sense of whether that's really that bad or how bad it is, or and then eventually look at what we might be able to do about it. So how are we going to figure out what's actually going on when we do this? A convenient answer is usually just simulate some data, right? When we simulate data, we know what the answer is going to be because, well, we put it there, right? So that's what I did. I simulated a data set with 15 variables, the first 4 of which actually contribute to the outcome to varying degrees. So you can see that there's some with fairly high contributions to the outcome and others with smaller ones. And then there's a whole bunch of variables that really don't do anything. And I set this up to have a pretty small sample size, so only 20 participants. And then I simulated some data from this, repeated it 1,000 times, and went ahead to fit 3 different regression models. The first one is what I call the true model, which only contains the first 4 variables that actually contribute to the outcome. Then there's the full model, which has all 15 variables just chucked in there, which in this case we can just about manage. And then I use a third model where I used forward selection to select a subset of variables. Usually, I wouldn't really recommend that you use forward selection, but it was kind of convenient in this case for demonstration purposes. And so what that does is simply it starts with a model with no variables in it, and then step by step adds one variable at a time, choosing the variable that seems to improve the model the most, right? Until it doesn't really improve anymore. All right, so having these simulation results, clearly what we are looking for is estimates of the 15 coefficients that are reasonably close to the truth, right? And also of particular interest, of course, is the sort of conclusions that these might lead us to, which is we got to look at how often these first 4 coefficients with actual contributions are deemed significant, and often we might miss out, and similarly how often the other 11 coefficients that ought to be 0 are deemed significant incorrectly, and give us wrong answers. So the estimates here, I've just plotted all of them. These are the first 4 coefficients, and you can see how they produce estimates of close to the real values, but spread out a bit. And well, I think this might be easier to see if we just look at these estimates after subtracting the real values, right? So this is basically now the errors of these estimates around the true coefficients. And as you can see, these, well, at first glance, they look kind of similar. One thing that maybe stands out is that there's quite a bit more variance in the estimates for the full model, which is the one in the middle. And you can see how these are more spread out, especially it happens to be especially pronounced for the third here, right, where there's a lot of variation here. Certainly a lot more than in the true model, which generally does best, unsurprisingly. And another thing you can see is that for the smaller coefficients, x3 and x4 here, it sometimes happens that these don't end up in the model, and then I've plotted them as 0 here, which happens here and here. So these are missed quite frequently. And if you look at this in sort of summary, right, just counting how often they made it into the model or not, you can get a sense of the different power you get from these different models to detect effects of these sizes. And in all of the models, the larger effects here are easy to detect. And then the smaller ones are a bit harder, unsurprisingly. It's quite a small sample. But you can see that the full model does especially poorly here, which is really where this sort of extra variance you get from chucking all the variables at it bites you. And so from this perspective, the forward selection here seems to do quite well, right? It did as good as the true model, really, maybe even better. So that doesn't look so bad, right? Of course, the real problem only arises when you then go and look at all the other coefficients that ought to be 0. Again, a lot of them are in the sort of forward selected model are actually 0, or rather are not included in the model a lot of the time, but sometimes they are. And when they are included, which is all the ones up here and down here, when they are included, they tend to have relatively large coefficients, which is why they were included. And you end up with quite a lot of false positives this way, as it turns out. So again, you can see what happened here after summarizing over these 1,000 simulations. That and I should say I'm not showing you the results for the true model here because they're all 0, right? They were never included in the model. You can see for the full model, each of the coefficients is included about 5% of the, or not included, deemed significant about 5% of the time, which is what you would expect when you use a p-value threshold of 0.05, as I did here. Sometimes they're slightly large, but it looks about right. For the model with forward selection, it's a lot worse. These error rates are 3 to 4 times higher than what you would expect. And that's not good news, right? It's pretty clear that this procedure has included variables without any real effect on the outcome fairly frequently, and not just included them, but they then end up being significant, and you might go look at that model and get all excited about I don't know, X13 and start to make up hypotheses about how that might affect your outcome, when in reality there's absolutely nothing going on, right? So that's bad, and it's going to happen a lot more frequently in situations where you do what I've done here and mix model selection with inference. So this is a example of how things can go wrong. And I hope that we can kind of agree that this is probably not what you should do. But still, it's kind of not very satisfying, right? Because in practice, you have this data, and you do want to get some answers out of it. So what do you do? Well, let's consider our options. The well, first option, which is maybe not very helpful, is to say that, well, you should do what you're supposed to do and decide on which model you're going to use before you look at the data, right? And if you do that, all is fine, obviously, but that doesn't really tell you how you're going to arrive at the model in the first place, so that's not really helpful in a situation like this. The second option is you could split your data set, right? So if you have enough data, you could take part of your data, so put it aside for later, and take the remaining bits to do all your model selection, figure out which variables should go in the model, which ones to throw out. and then take that model and apply it to the remaining data and use that to answer your research questions. You can either do that by collecting all the data up front, or possibly even better, have a second round of data collection for that, which in some cases is something that's commonly done, where you kind of have an exploratory study first and then a confirmatory study where the model is basically fixed and you just try to confirm the effects you think you might have found some evidence for. So that's something you can do if you are lucky enough to be able to, in a situation where you can afford that. Another option is that you could, if you can, select the variables that go into the model without ever looking at the response, you'll be fine. So really, what this means is that the actual problem arises when you do model selection, and that typically includes looking at your response, right? Because that's what you're modeling, that's what you're selecting a model for. And then everything gets difficult. But if you can somehow choose which variables to include without doing that, without sort of contaminating your response, if you like, then you're fine, and bad things should not happen. Of course, that sounds like another not very helpful response, or not very helpful option here. In some cases, it can be helpful. One situation is if the main reason for you to want to do variable selection is that you feel you need to deal with collinearity, right? If you have lots of related variables and you kind of need to decide which one's going to go in the model and which one you're going to throw out. You can look at variance inflation factors, for example, to decide which variables are maybe problematic and should be excluded. And you can do that without needing to look at the response. So that might be helpful. There are other situations where you might do something like this using sort of factor analysis type approaches to create a new set of variables that you'll then include in the model. And that would also be fine. But it's not always what you want, and especially the later of these, if you create sort of factors to include rather than the original variables, it can be really hard to interpret, which then might not be great in terms of answering your research questions. So another option you could pursue is to adjust the p-values you get from your model to account for the effect of model selection, right? So the idea there is that, yes, we have looked at the data and we have selected the variables that kind of looked best at explaining what's going on, and that is likely to inflate false positives because we kind of cherry picked the variables that looked significant, right? And sometimes that will just be due to noise. So if we can understand how this selection process affects our p-values and makes them too small, then we could basically apply some sort of correction, if you like, to get more accurate p-values. And then we could do inference again and things would be all fine. And over the last several years, quite a lot of people have thought about this and have developed methods to do this. Some of these methods are available in an R package called selective inference, which you might find useful if you want to do this sort of thing. So that sounds more promising. But let's take a look what actually happens, right? I mean, we already have some simulated data, so let's see what happens if I now go and apply this correction here. And so this is the same table you saw before for the coefficients that actually are supposed to be 0. And now I've added a column here for the p-values that have been adjusted for that selection process. And then again, I've counted how often these coefficients turned out to be significant. That is a lot less now, as you can see. So these numbers are quite a lot smaller. And as it turns out, they may be a bit too small. Remember, we are looking for something like 0.05, and these are definitely less than that. So this looks like, yes, it has dealt with the problem of inflated p-values or inflated type 1 error. But maybe it has gone a little bit too far the other way. And now our test is too conservative, basically. And if you look at the coefficients, the non-zero coefficients that actually should have some real effect, and how often they were significant in the models, you can see that that effect actually turned out to be fairly pronounced here, with even the two larger coefficients not always making the cut, if you like. And of course, it looks particularly bad for the smaller ones, which is not that surprising. And so I think the conclusion from this is that methods like this can help. They will help you deal with the fact that your model selection has made inference a bit tricky, and it will take care of that difficulty for you to some extent. But it does come at a cost of power, which essentially means that if you want to do this, you'll need a larger sample. And you should account for the fact that you have this analysis procedure that includes model selection and then inference from the same model upfront. So you can make sure that there is sufficient data to actually do this. Because otherwise it looks like it is quite likely to go wrong, one way or the other. And yeah, but I think there's a bit of good news at the end in that it is in fact possible to reconcile a model selection and inference if you want to. But you do have to be a bit careful about how you do it. And yeah, make sure you get it right. And that's all I have today, but we should have time for some questions, which you can either type into the chat or unmute yourself and just.
There is one question in the chat from Jason. Can you include a fake variable that you know the outcome and see how the inference selection thing is behaving?
Yeah, or so you mean with your real data include something where you know what's going on? I don't think I would recommend it, because you still don't know what's going on with all your other variables where that you actually care about, and actually including something extra might affect the estimates you get for those. So that's probably not something I would do. It's easy to do these things with simulated data, right? And that's all well and good to get a sort of general idea. But the problem with your real data always is you don't know what the real answer really is. And you kind of have to live with that uncertainty. All you can do is try to get the sort of methodology right.
Okay, there's another one. This is from Craig. Thanks for the presentation. I'm wondering if the bias induced by variable selection is less of a problem if you are selecting from a reduced set, for example, 3 variables from a total of 5, rather than in your example.
Right. So I think, yeah, I mean, the smaller the number of variables is to begin with, the easier problem it is. Overall, I think that is true. And I should probably have mentioned another option, another possibility for variable selection that's entirely valid, which is expert knowledge, right? So if you know which variables you want to include, then obviously you should go and do that. Yeah, so fewer variables does mean that there's less of a problem, I think, in general. And of course, the more variables you have in your data set that have no real contribution to the outcome, the worse it is, right? And it's entirely possible to have lots of variables that all are somewhat related to your outcome. So in that case, you wouldn't strictly get false positives necessarily, but you would still potentially severely overestimate the effects of individual variables.
Okay, another question from Paris. How about using a reduced model of analysis? She means by removing a variable at the time to see the significance of the contribution of the remaining variables.
Yeah, well, then you are maybe doing something along the lines of backward selection, right? It's just a different way of variable selection. Which, and I mean, generally, I would favor that over, say, forward selection, but it doesn't solve the problem. You still have the issue that you will end up with variables in the model that look to have a particularly strong relationship with the outcome in your particular data set. And some of those may well have no real effect, right? So that problem doesn't go away.
Okay. Are there any other questions? If also if you want to, you can unmute and just ask a question.
Yeah, so there was a question about
there we go.
Linear, well, how this applies in other models rather than just linear regression, which is what I talked about. I mean, the similar reasoning kind of applies, right? So one of the problems here is that you have a particular data set, and in your data set, it might look like variable X has a particular strong relationship with the outcome, but that might not be the case in general. And those sort of and that might then be emphasized even more if you end up including that and maybe excluding other variables that have a real relationship. That's, I think, a problem in almost any analysis method. And so you, well, I mean, you can think of sort of more complex things like, I don't know, structural equation models, which, well, really involves a lot of linear regressions again. But that's a field, or people working with structural equation models often do this quite systematically, that they separate model selection and inference by having a separate sort of validation study at the end. And yeah, so I don't know, was there anything in particular that you wanted to know about?
There's one other question. Does this problem also apply to interactions if you choose your main effects blind but do backward selection for the interactions?
I would think so. It may be, I admit I haven't really thought about this very closely, but it may be a bit less of an issue if you have chosen your the variables to include in some other way, and then only look at whether or not to include interactions between them. But again, there will be an issue that sometimes in your data it will look like there might be an interaction between these two variables when in reality it doesn't exist. And you then essentially sort of you overinterpret that, if you like. You put too much weight on the existence of that interaction because you have no way of validating that outside your data set, unless you go and validate it.
Peter, this problem, I mean, I don't know if this is an absurd extreme, but it could apply to something like a one-way ANOVA in a sense. If you're looking at whether a particular factor affects an outcome, and you then are interested also in the means of the levels in that factor, you're doing a model selection routine in a fairly simple way, and then moving on to inference as well after that. So what sort of range of analyses do you think this becomes a problem in?
Yeah, so I mean, I think it's the main problem arises when you have lots of variables and you try to pick and choose from them, right? Because you're sort of cherry picking the biggest effect. With the ANOVA, well, I guess you could have a one-way ANOVA with lots of groups, which could run into a similar problem. But if you but I mean, if you have something like a few experimental groups, right, in your ANOVA, and then do comparisons between those, or looking at their means, I think there you're probably fine. And of course, if you do sort of post-hoc comparisons, you probably should correct for multiple testing, and in a way that will take care of your p-value problem there. And so in a way, I think you can think about this issue as the model selection, certainly sort of in the linear regression example, essentially doing lots of hypothesis testing without actually accounting for it properly. Right, and then if you do it a bit more out in the open, as you do maybe with an ANOVA and then post-hoc comparisons, then you know which test you've done and you can apply suitable corrections, and I think then you're fine.
Great, thanks.
Okay, I think that's all the questions that we had. Thank you so much for everyone for attending. We'll have another one in March. We don't have the date quite yet. And I think we're going to be talking about meta-analysis, or at least Xixin will. So thank you very much, and keep an eye out for our next seminar.